There is a fundamental tension between what we see in the Boötes Void and what the laws of physics demand should be there. If you take the standard cosmological model, the blueprint for how the universe built itself from the fire of the Big Bang, the Boötes Void is a mathematical impossibility. It is a 330 million light-year error. According to the timeline of gravity, there simply hasn't been enough time since the beginning of the universe for a region of space this large to empty itself so completely. It is as if we found a cathedral that was built in a single afternoon. The growth problem haunts the study of large-scale structures. In the early universe, matter was nearly uniform, with only tiny fluctuations in density. Gravity acted on these ripples, pulling gas and dark matter together to form the first stars and galaxies. Voids are the natural byproduct of this process, the empty spaces left behind as matter migrated toward the high-density nodes. But gravity is a slow, methodical worker. For a void to reach the diameter of Boötes, it would have to have started clearing out matter at a rate that defies our understanding of cosmic expansion. When we run supercomputer simulations of the evolving universe, such as the Millennium simulation, we see thousands of voids forming. Most are small, bubbles only tens of millions of light-years across. Occasionally, we see larger ones, but they are usually noisy, filled with thin filaments of dark matter and failed galaxies. The Boötes Void, however, is unnervingly sterile. To replicate its existence in a simulation, you have to tweak the initial conditions of the Big Bang to an extreme degree, or you have to introduce a force that clears the space faster than gravity alone. This has led to the void merger hypothesis, a theory born out of professional discomfort with the data. It suggests that Boötes isn't one void, but a collection of smaller voids that have popped together. Think of it like a cluster of soap bubbles in a sink. As the bubbles expand, the thin walls of galaxies between them are stretched until they reach a breaking point. When the wall snaps, the galaxies are violently accelerated toward the outer edges of the new, larger void. But even this theory has a flaw. If a merger of this magnitude occurred, we should see the wreckage. We should see debris fields of shredded galaxies and tidal tails of gas lingering in the center. We don't. We see a vacuum so pristine, it looks like it was swept clean. The 60 galaxies we do find in the interior are not wreckage. They are survivors, sitting in the middle of a perfect, empty sphere. There is a specific measurement in cosmology called $sigma_8 which describes the clumpiness of matter in the universe. The Boötes Void represents a massive deviation from the expected $sigma_8 value. It is a region where the clumpiness is zero, or near zero, over a distance that represents a significant fraction of the observable horizon. When astronomers look at the Boötes data, they aren't just looking at a hole in space, they are looking at a hole in the theory. The presence of the void suggests that our understanding of dark energy, the mysterious force driving the expansion of the universe, might be incomplete. If dark energy is stronger in certain regions, or if it interacts with dark matter in ways we haven't yet mapped, it could act as a void driver, pushing matter out of these regions with more efficiency than gravity pulls it in. In this light, the Boötes Void isn't just an empty room. It's an active laboratory where the laws of the universe are being pushed to their breaking point. We are left with a choice. Either the Boötes Void is an extreme statistical fluke, 1 in a billion, accident of cosmic birth, or our map of the universe's history is missing a chapter. There is a quiet, professional unease among those who spend their lives looking into the hole. They are looking at a void that shouldn't be there, measuring a silence that shouldn't be this quiet, and realizing that the more we learn about the great nothing, the less we understand about the big everything. The internal structure of the Boötes Void is a study in impossible geometry. In most cosmic voids, there is a gravity gradient, a subtle shift in the density of matter as you move from the rim toward the center. It usually looks like a bowl, with galaxies becoming sparser toward the bottom. But Boötes does not look like a bowl. It looks like a plateau of nothingness. The vacuum is flat. Once you cross the threshold of the Great Wall and enter the interior, the density of matter drops to a near absolute minimum and stays there for hundreds of millions of light years. This flatness is a signature of what cosmologists call a deep void. Implies that the region has reached a state of maximum expansion. In the early stages of a void's life, it is a protovoid, a place where matter is still being drained. But Boötes has moved beyond that. It is a mature structure. It has exhausted its supply of matter to export. Every star, every cloud of dust, and every particle of dark matter that could be moved by gravity has already been shelved into the surrounding walls. One of the strangest features of this architecture is the velocity flow of the galaxies on its perimeter. Because the void is so empty, it acts like a giant low-pressure system in the weather of the cosmos. Galaxies near the edge are being sucked away from the center at speeds that exceed the general expansion of the universe. This is the peculiar velocity of the void's shell. To an observer inside the void, it would look like the rest of the universe is fleeing in a desperate, coordinated retreat. but it is the intervoid filaments that present the most disturbing data. In 2001, a deep survey study attempted to find the skeleton of the void, the thin dark matter bridges that should, theoretically, connect the internal galaxies like the spokes of a wheel. They found almost nothing. Where there should be a network of gas and dark matter, there is only a pervasive, cold transparency. The filaments that exist are so thin and so stretched that they are essentially translucent to our instruments. This structural integrity, the way the void maintains its shape without internal support, suggests that dark energy is the primary architect here. In the voids, dark energy is the dominant force. Without the anchors of dark matter to slow it down, the expansion of space inside boats is purer than it is elsewhere. It is spacetime in its most raw, unadulterated form. If you want to see what the entire universe will look like in 1 trillion years, you look here. You are looking at the final stage of the cosmic life cycle. There is a specific kind of galaxy found near the center of this vacuum, the void galaxy. These are not just normal galaxies in a different location. They are often stunted, they are smaller, with less complex chemical structures, because they have never had the opportunity to merge with others and recycle their stellar material. They are primordial, they are the evolutionary equivalent of a species trapped in a cave for millions of years, developing in complete isolation from the rest of the world. When we analyze the light from these central galaxies, we find a high proportion of population to metal-poor stars that formed shortly after the Big Bang. In the rest of the universe, these stars are buried deep inside the cores of massive ellipses. In the Boötes Void, they are the main event. The void has acted as a preservative, keeping a small slice of the ancient universe intact, frozen in a state of arrested development while the rest of the cosmos moved on. But even this preservation is a form of decay. Without the influx of new gas from the cosmic web, these galaxies are slowly running out of fuel. They are closed systems. They are dimming. The architecture of the vacuum is a trap. It allows a galaxy to exist in perfect peace, but it denies it a future. The void is not just a place of no matter. It is a place of no potential. It is a closed room where the oxygen is slowly being replaced by a silence that will never be broken. In the early 1990s, the Cosmic Background Explorer COBE satellite returned a thermal map of the infant universe, captured just 380,000 years after the Big Bang. Most of the map was a static-filled hiss of nearly uniform heat, but in certain coordinates there were bruises, regions slightly colder than the average temperature. One of these anomalies aligns with the Boötes Void. It is a signature of energy loss that challenges our understanding of how light interacts with the geometry of nothingness. When a photon of the cosmic microwave background, CMB, enters a region of high mass, such as it gains energy as it falls into the gravitational well. As it exits the other side, it loses that energy. In a static universe, the gain and loss would cancel out. But our universe is expanding. By the time the photon tries to climb out of the well, the expansion of space has stretched the well, making it shallower. The photon exits with more energy than it had when it entered. This is the integrated Sachs-Wolf effect. In the Boötes Void, the opposite occurs. A photon enters a region of extremely low density at gravitational hill. It loses energy as it climbs the hill toward the center of the void. Because space is expanding while the photon is mid-transit, the hill flattens out. When the photon finally descends the other side, it doesn't get all its energy back. It emerges, tired, redshifted, and colder than its peers. The Boötes Void literally drains the heat from the beginning of time. However, the temperature dip recorded in the direction of boats is deeper than the math allows. If the void were simply a hole filled with a standard vacuum, the cooling effect should be minimal. The cold spot suggests that either the void is even emptier than our galaxy counts suggest, or it is much larger than its 330 million light-year diameter. Some theorists propose that we are seeing a supervoid that extends far beyond the observable light, a structure so massive it shouldn't have been able to form under any standard model of gravity. This energy drain has led to a controversial line of inquiry, the possibility that the Boötes Void is a point of contact. In certain brane cosmology models, our universe is a three-dimensional membrane floating in a higher dimensional bulk. A void of this magnitude could theoretically be a collision scar, a place where another bubble universe nudged into our own, displacing matter and leaving a permanent chill in the cosmic radiation. It is a radical thought, born from the desperation to explain why a whole of this scale is so devoid of the features that define the rest of existence. We also have to contend with the missing baryons. Observations of the universe suggest there is far less normal matter, atoms, gas, stars than there should be based on the Big Bang's nucleosynthesis. Many looked to the voids as the hiding place for this missing matter, vast, invisible clouds of diffuse ionized gas. But the spectroscopic data from Boötes remains stubbornly clean. If the missing matter is there, it is so thinly spread that it doesn't even leave a fingerprint on the light. Passing through it, the void isn't just a lack of things. It is a lack of information. In the rest of the sky, the CMB provides a blueprint for the structures we see today. But the Boötes region is a disconnect. The seed that should have grown into a modest cluster of galaxies instead grew into a colossal exclusion zone. We are looking at a localized failure of the universe to follow its own instructions. As we refine our measurements of the cold spot, the tension only grows. The void appears to be hollower than a vacuum. It is a region where the expansion rate is winning so decisively that even the most fundamental particles of light cannot pass through, without being stripped of their vitality. We are measuring a shadow cast by an absence, and the shadow is larger than the object that should be casting it. The Boötes Void is a preview of the end of everything. In the field of thermodynamics, entropy is the measure of disorder, the inevitable slide toward a state where energy is so spread out that nothing more can happen. Most of the universe is still young and chaotic, a place of high-energy collisions and gravitational clustering. But the void is different. It has already arrived at the finish line. It is a pocket of the universe that has achieved a state of near-terminal equilibrium. In a standard galaxy cluster, gravity creates negative heat capacity. As things fall together, they speed up and get hotter. But in the void, the expansion of space has reached a velocity that gravity cannot match. This creates a cooling that is more than just thermal, it is structural. The expansion acts as a heat sink, stretching out the wavelengths of any stray radiation until they are functionally not. If you were to place a thermometer in the darkest part of the boat's interior, you would be measuring a temperature that is as close to absolute zero as the laws of physics allow. This leads to the evolutionary dead end for the galaxies trapped inside. Normally, a galaxy grows by feeding. It draws in cool gas from the intergalactic medium, or it merges with smaller dwarf galaxies to replenish its supply of hydrogen. Inside the Boötes Void, there is no food. The 60 galaxies we see are starving. They are passive systems, or red and dead in astronomical parlance, though some still show a frantic, final burst of blue light from their remaining reserves. Once they burn through their current gas, they have no way to get more. They will not merge. They will not collide. They will simply fade. There is a profound unease in this realization. We are used to a universe that builds. We see the Hubble Deep Field and we see a factory of light. But the Boötes Void is a factory of deletion. It suggests that the cosmic web, the beautiful, interconnected structure of the universe, is not a permanent fixture. It is a temporary phase. As the voids grow, they break the connections. The Boötes Void is the first major rupture in the fabric, a place where the web has already snapped and the loose ends are drifting into the dark dot. As we monitor the movement of the galaxies on the edge of the void, we see them being pulled away from the center at millions of miles per hour. This isn't just movement, it's an evacuation. The void is clearing its territory. There is a mathematical limit known as the turnaround radius, the point where the expansion of a void becomes so powerful that nothing can ever fall back in. Boats passed that point hundreds of millions of years ago. It is now a one-way street. Anything that leaves the void can never return, and anything inside is destined to stay there until it vanishes. The unresolved escalation lies in the growth rate. Recent data suggests the void is expanding faster than the surrounding universe. It is a runaway process. Because the density inside is so low, there is no gravitational brake to slow down the dark energy driving the expansion. The less matter there is, the faster the space expands. The faster the space expands, the less matter there is. It is a self-reinforcing cycle of erasure. We are looking at a structural failure that is contagious. As the Boötes Void expands, it will eventually touch other, smaller voids. When they merge, the combined expansion will be even more violent. We are witnessing the beginning of the Great Thinning. The Great Nothing isn't just a static feature of the map. It is a growing shadow. It is the future, leaking into the present. And as the signal from the center grows weaker, we have to ask ourselves, how much longer do the walls have before they, too, are pulled into the vacuum?